Okay, I want to tell you about Gauss's law on coaxial cables. Coaxial cables, that means that there's two cylinders or a wire and another cylinder that are on the same axis. They're coaxial. They have the same axis. This is a coaxial cable. You know, you use them all the time. That's what you might hook up your television set to get cable television. That's a coaxial cable. You can't see this very well on here because it's so small. But there's a wire coming in here. There's a wire there, and then that runs through the center of this wire, and then there's another cylindrical wire that goes around the edge, and so you can run current up and down here, or charge it up and look at the fields. Now we're going to say there's air between the center wire and the outer wire, but really there's some plastic or something. That's how they are able to keep it from the two from touching. It'd be really tough to do if there wasn't plastic there. Also, we're going to assume the cable is incredibly long, but it turns out that the approximation you get when you don't make it that long, when you make it say this long, it's almost dead on with the equation when you assume it's long. It's kind of like the simple pendulum. A simple pendulum, the equation has an approximation in it, but it's pretty close to being right on. All right, so here's a coaxial cable, and we're going to say that this has a linear charge density of lambda. Lambda is the charge per length. And so here's the wire going this way, and it's got a linear charge density of lambda. And then there's some air here. This is air right here. And then if you go out to A, that's the inner radius of the outer cylindrical shell. So this is a cylindrical shell wrapping around. It's kind of tough to get just the setup in your mind, but this is metal, and it's got some thickness. See how it runs from A to B, B being the outer wall of this cylindrical shell. Okay, and so let's see. There's a few things that they're going to ask us to do. They're going to ask us to find the electric field at, say, this point. They're going to want to know the electric field inside the metal. They're going to want to know the electric field out here. They're also going to want to know what the charge per length is for the inner surface, the lambda for the inner surface, and the lambda for the outer surface. Let's assume that the net charge on this shell, the cylindrical shell, is 0. So there is no net charge on the outer shell, let's say. Okay, so let's figure out then how you'd get the electric field, say right here. The electric field at R, we want to go where R is less than B. So I want to find the electric field, that's a colon, where R is less than A rather. So R is less than A. Okay, so that would be this is R. That's lowercase r. Okay, so I'm going to draw a Gaussian cylinder. And it turns out that there's two ways to find the flux through here. One way is just to get the charge enclosed. Well, the charge enclosed over epsilon naught, that's one way to do it. Another way is to find the flux is to find the E dot dAs for every point on the surface. Okay. Well, the electric field here is going to go from, if this is a positive charge per length, and we're assuming that it is, then the field lines look like this. They're radially outward, cylindrical though, but they go out, they branch out like that. And so there is no flux through the top and the bottom of the cylinder. There's just flux out the sides. And so let's see, the total charge enclosed, if I call the height of this Gaussian cylinder h, the total charge enclosed would be just how much lambda, how much charge we have per length times the length. So it would be the, pardon me, it would be lambda times h. That is the total charge enclosed. When you multiply this quantity by a length, the lengths cancel and you just get Q. Okay, now we can get rid of the dot product here on this side because the E and the dA's are always in the same direction. And I can pull the E out of the integral because it's the same at every location on here. Why would we expect E to be bigger here than here, than here, than here? It should be the same. And so when I do that, it's just going to say sum up all the dA's. And if I sum up all these dA's, that would be like cutting this and rolling it out. That's the area of the sides. And the area of the sides is going to be 2 pi r times h. Yeah, if I rolled this out, it might look something like this. And all these dA's, see all these little dA's? When I add them all up, I just get 2 pi r h. Okay, so we can cancel h out of there. And so the electric field inside is going to be lambda over 2 pi r epsilon naught. Okay. Okay, what about in here? What about the electric field in here? Well, that's a metal. So this is metal. So any metal that's in electrostatic equilibrium has to be equal to, the electric field has to be 0 in there. So E, where R is greater than A, R is greater than A, but it's less than B, the E is going to be, the E will equal 0. Now I'm not using Gauss's law to get that done. I'm just saying that that's a metal, and if it weren't 0, if the E were something other than 0, the charges would be moving around. So that's not electrostatic equilibrium. And so so that's how you solve that. There's not much to solve. All right. So the next thing is now we want to get the outside. So what would be the outside? Well, there's no net charge on this thing. And so the outside, if I wanted to know the field there, I'm just going to put a Gaussian surface here. A cylinder, like such. And with that cylinder, there's no flux on the top and the bottom. But you know what? The net charge enclosed is going to be, again, there's no net charge on this outside cable. So the net charge enclosed is going to be just, again, lambda h. It's just this charge that's in here. So if you want to get that, the E, when you're outside, is going to be lambda h over epsilon naught is equal to, I can get rid of the dot product because E and dA are in the same direction. And when I do that, I can pull the E out of the integral because the E is the same at every spot on here. It's the same at every spot on the Gaussian surface. So this just turns into E times 2 pi r h again. Different r, it's a bigger r. But the h's cancel, and I get the same equation as this up here. Okay, I'm going to have to break this into 2 videos, so we'll see you in the next video.